if we think about this potential energy, for any given r, the potential is the same for a given r. And so if we put the proton at the middle of a sphere, then any point on the surface of that sphere has exactly the same potential. And so this potential energy is spherically symmetric. That means that it's going to be best to solve this problem using spherical coordinates. Before we start writing our Hamiltonian in polar coordinates, let's take a look at the reduced mass between the electron and the nucleus. So the reduced mass between the electron and the nucleus is the mass of the electron times the mass of the nucleus divided by the mass of the electron plus the mass of the nucleus. And the mass of the nucleus is much, much greater than the mass of the electron. And so if we have a very big number and we add a tiny, tiny number to that, we have essentially just this big number. And so we can approximate this to a very high degree as just equal to the mass of the electron. And in general, the mass of the electron times the mass of the nucleus divided by the mass of the electron plus the mass of the nucleus, for the nucleus just being a proton, is going to be equal to 0.9995 times the mass of the electron. And so we can see that this is very close to just the mass of the electron. And as we get to heavier and heavier atoms with larger and larger nuclei, this approximation becomes even better. And so we aren't going to have to use reduced mass coordinates. We can think of the proton as being stationary and the electron moving around that proton. So if we're going to solve this problem in spherical coordinate systems, we need to write down what del squared, the operator for the gradient, is equal to in spherical coordinates. And this is equal to 1 over r squared, partial with respect to r squared, partial respect to r, plus 1 over r squared times the quantity second derivative with respect to theta, plus cotangent theta derivative with respect to theta, plus 1 over r squared sine squared theta derivative, second derivative with respect to phi. Recall that we defined in polar coordinates the angular momentum squared operator as equal to minus h bar squared times second derivative with respect to theta plus cotangent first derivative with respect to theta plus 1 over sine squared theta second derivative with respect to phi. So if I factor an r squared out of these two terms and write del squared as equal to 1 over r squared, derivative with respect to r squared, derivative with respect to r, plus 1 over r squared times second derivative with respect to theta plus cotangent theta first derivative with respect to theta plus 1 over sine squared theta second derivative with respect to phi, then I can see that this can be expressed as minus L hat squared over h bar squared. This will simplify our Hamiltonian because we've already solved this problem when we solved the rigid rotor. So let's write our del squared operator in terms of that angular momentum operator. So we still have this dependence on r minus L hat squared over r squared h bar squared. So now when we write our Hamiltonian, remember that we want minus h bar squared over 2 times the mass of the electron, del squared psi plus v psi equals e psi. So we're going to multiply r del squared by minus h bar squared over 2 times the mass of the electron. So we have minus h bar squared over 2 mass of the electron r squared, derivative with respect to r, times the quantity r squared takes the derivative with respect to r of psi, minus the h bar squareds and the negative sign cancel, so plus L hat squared over 2 mass of the electron r squared operating on psi, plus V operating on psi equals E psi. So this is then the differential equation that we need to solve, and we know that psi is a function of r, theta, and phi. And remember that all of our angle dependence is contained in this L squared operator.